Okay, let's look at parametric equations again, but let's make our focus the calculus piece of it. So again, x of t is our horizontal position as a function of time, and y of t is our vertical position as a function of time. Again, this is describing the motion of an object. Okay, so how does the calculus play a role? Well, we can take derivatives of x of t and y of t, right? We can find dx dt and dy dt. And again, what are those things? Well, in a physics classroom, we would just call that v subscript x. It's just the horizontal velocity. Well, dy dt, remember, it's the derivative of y with respect to time. It's the rate at which this is changing. Well, that's the vertical velocity as a function of time. We can take another derivative, which typically we would call x double prime. We can take another derivative of this with respect to time, which we might call y double prime. These are just horizontal acceleration and vertical acceleration. Those are pretty easy. That's just take x of t, take a derivative with respect to time, take another derivative. I mean, that is the definition of velocity. It's the rate at which you change position. Acceleration. The definition of acceleration is the rate at which you change your velocity. It makes sense that the derivative of velocity is acceleration and the derivative of position is velocity. This is just in horizontal and this is in vertical, so we have components. They might talk about the velocity vector. They might say something like the velocity vector, and again, it would be in this notation in a calc class. These symbols kind of tell you that it's a vector. The acceleration vector is just x double prime comma y double prime. Okay, and those are typically easy to find. You can ask for the velocity vector in the abstract, so these would just have times in them, or you can say, what is the velocity vector at 2 seconds? What's the acceleration vector at 3 seconds? You know, if they give you a specific time, then these are just two numbers. This is like 3 comma 4, and you're giving me these brackets to indicate that it's a vector. Okay, so one of the other things, early on, they might talk about the speed. Again, we're interested in how fast the object is moving at a given moment. Well, if you looked up the formula, the speed is going to be dx dt squared plus dy dt squared. And I want to make sure you understand why. That's really easy. This is just the Pythagorean theorem. So what is speed? Well, speed is the magnitude of the velocity vector. It's how fast you're moving. Now, velocity is a vector, which just means it's got components. At any moment in time, you're moving horizontally, and you might be moving vertically, right? This is just your horizontal velocity, dx dt, and this is your vertical velocity, dy dt. Well, the speed is the length of that vector. That's your actual velocity vector, and those are your pieces. Well, the magnitude, meaning the length of this arrow, is just the Pythagorean theorem. It's just the square root of this squared plus this squared, and then we have our speed. So speed, this formula, isn't anything more than just the Pythagorean theorem based on this particular triangle. Okay, so we look at speed. Well, if we look at speed, then we'll also look at distance. The distance an object travels. Distance is different than displacement. We'll talk about displacement in a second. The distance is the total distance an object would travel along its path. So we could look at a y versus x graph. This could start, let's say at t equals 0, it's over here, and it goes north, and then this way, and then this way, it ends up over here. And again, we want to figure out the total distance the object travels, and we use calculus to do it. Distance, old school, was a rate times a time, and that's still what it is. We just have to divide this path into really, really, really small time intervals. Each one of these little increments are dt in terms of the seconds. But if you tell me that we're going to break this up into really small time intervals, and you tell me the speed at which the object is traveling at every single moment, and you take the speed times that moment, that's the distance it travels in that moment. But if you sum up, which is our integral symbol, all the different distances, again, let's sum up all the speeds times time. If you take all the individual speeds times time, this quantity represents the distance traveled in that time interval, and all you want to do is then sum up all of those individual distances to find the total distance. That's the whole purpose of what an integral does. The integral accumulates speed over time. So these formulas are obviously really related in terms of you understand that this calculates speed at any moment, then the integral just sums up the speed and calculates the distance traveled over that time interval. Okay, so we start talking about speed and distance. Then we also need to start talking about displacement. Okay, displacement. Displacement is different than distance. Displacement is a vector. Okay, this bad boy is a vector, which means we don't talk about the displacement, we talk about the horizontal displacement and the vertical displacement. And we can use those things to say where an object is located, and that's the position. I know these three words are kind of used interchangeable, but the position of an object is its location. The position is the location, distance is the total path length that you would walk, and the displacement is the change in x and y. Okay, so let's say you were given dx dt and dy dt, and you wanted to figure out where you're located. Okay, so let's say you knew dx dt and dy dt, and you want to figure out, where am I at a future time? Well, think about what x can be. X of t. X of t can be written as like x of 0 plus the accumulation of from 0 to t of dx dt times t. There's your position function written in calculus. And again, let's assume that this is a fairly complicated equation that we can't just integrate, find c, and then plug in. Let's say we can't actually find an integral. However, we can do a definite integral because our calculator can do it for us. So think about what this is saying. This piece right here is delta x. Think about why. What are we doing? We're accumulating horizontal velocity over time. Well, if you accumulate horizontal velocity over a time period, you get the change in your horizontal position. And if you add the change in your position, this quantity, to where you were, you're going to figure out where you are now. Again, this is some future time. If you want to know x of 5, starting at x of 0 plus what you did from 0 to 5. What you did from 0 to 5 is accumulating your horizontal displacement. If you wanted to know your vertical position, we'll just take some starting vertical position plus what you did vertically. And again, that's accumulating dy dt over a certain time period. And you may not even know x of 0. You might know your position at 2 seconds. Well, x of 2 plus 2 to t. This doesn't really matter what value you have. As long as you have some position, some initial value, you can accumulate horizontal velocity to find a horizontal displacement, and then add, or even if you go back in time, you can even subtract to figure out some past position or a future position. Again, these are related, right? The displacement is completely component form, meaning just the part. Horizontal displacement gives you some idea to how to figure out a horizontal position. Distance is thinking about both of them at the same time. It's literally the total path length. It's the arc length of the curve. It's if you started here and you ran along this hiking path, how many meters did you travel? This. This is just the difference between the start and the end, and the start and the end vertically. They're different, and again, you have to kind of think about the differences between distance traveled, displacement, which is a vector, it's got pieces, and then the final position is just a location. Where are you at 5 seconds, horizontally and vertically? Okay, let's take a look at a couple other things. Okay, let's look at the slope on a graph like this. Okay, so we know what slope is. Slope is, and always will, just be dy dx. And the question is, if your equations are defined parametrically, how do you find dy dx? Well, think about it. you're moving horizontally and you're moving vertically. This is how fast you're moving horizontally. This is how fast you're moving vertically. If you want to find your slope, right, this is what you're actually doing. That's your path. Slope is what it always is, rise over run. The slope, dy dx, is just the ratio of dy dt over dx dt. Again, it's no different in 2 dimensions than it was in a normal graph. If you're looking at a dy dx, if you're looking at a graph, dy dx is slope. Slope is the slope of this line. The slope of this line is rise over run. Okay, and the slope kind of tells you the direction you're moving, because it's comparing how fast you're moving vertically to how fast you're moving horizontally. This is not speed. I'll give you a quick example of why this is not speed. Again, it involves looking at dy dt and dx dt, but the slope involves the ratio. Speed is the Pythagorean theorem of these two quantities. I'll give you an example. Okay, so let's take an example where x is 4t and y is 4t. At t equals 0, you're at the point 0, 0. After 1 second, you're at the point 4, 4. Okay, so like you started here, and in 1 second, you went to here. Okay, what's the slope of this line? Well, 0, 0, 4, 4. This has a slope of 1, right? This has a dy dx equaling to 1. You're going just as fast this way as you are this way. Okay, if I change this, and I say, all right, let's do the change here. What if y equals 10t and x equals 10t? Well, that means in 1 second, you'd go from 0, 0 to 10, 10. Now, how do the slopes of the line compare? Well, the slope of the line is still 1, because the ratio of the speeds is still the same. In this case, you're moving 10 this way and 10 that way per second. So the slope is the same because these ratios are the same. However, this is way slower than this. Here, you moved from 0, 0 to 4, 4 in 1 second. Here, you moved from 0, 0 to 10, 10 in 1 second. This is way farther, right? 2.5 times farther than this. So this is 2.5 times faster. Well, why? Because here, even though the slopes are both 1, the speed here is dx dt squared plus dy dt squared. Here, the speed here is 10 squared plus 10 squared. The speed is much different, okay? So don't confuse speed and slope. Slope always is the same. It's just the rise over the run. In this case, it's dy dt over dx dt. Okay? Every now and then we're going to be interested in the angle at which you're traveling, which is talking about this angle here, that theta, which is the same as this theta. And again, how do we find angles? Well, it's just a triangle. We just use inverse tangent. Theta is just inverse tangent of the opposite over the adjacent. Well, the opposite, dy dt over dx dt, well, we typically already have that. We already calculated that somewhere in the problem. But what is that ratio? Well, that is the same thing as just saying inverse tangent of the slope. So regardless of which one of these you use, they're the same, right? dy dx is equal to dy dt over dx dt. So you can find the angle using either of these ideas. Okay? So we really got to hit the differences. On the first page, I was kind of trying to highlight the velocity vector, acceleration vector, and then the differences between distance, displacement, and position. And again, I introduced speed. On this next sheet, then I introduced dy dx, which is just slope, and made an argument that slope is not the same thing as speed. And then I also talked about finding the angle based on those quantities. Okay, let's find the second derivative. This is my least favorite one. It typically doesn't mean much in the discussion of motion, but what is the second derivative? That's kind of the funky way to say it. You can't say y double prime, because y double prime typically means vertical acceleration in this case. This is not acceleration, just like this is not speed or velocity. So how do you find this? Well, it turns out you just take the time derivative of dy dx and divide by dx dt. Now remember, this is not something times something. This is take the derivative with respect to time of this quantity. This is something that's like a function. It's like taking sine of something. This is the operator. It says take the derivative of this. So if you want to find this value, find dy dx first, take a time derivative of dy dx, and then divide by another dx dt, which is just the time derivative of x with respect to time. And we'll go over some examples with that. Okay, so it won't be too bad. Okay, let's go over a couple more things in terms of what things mean. Okay, so what would it mean if I told you that dx dt was greater than 0? Well, that means your horizontal velocity is greater than 0. That means you're moving to the right. Now you have no idea what you're doing vertically, okay? But if you know this is true, that is what's happening. You're moving right, okay? You don't know if you're moving this way, or you could be moving this way. You just know that your horizontal position is increasing, and so you know you're moving right, okay? What if you knew that this was true, and you knew that dy dt was less than 0? Well, then you'd be moving right, and you'd be moving down, and so you know you're doing that. Okay? How would you decide if you were moving straight up? What would that mean? Well, what is moving straight up? Well, it would be a positive dy dt, and it would be a dx dt equaling to 0. Because you can't be moving horizontally, and you have to have a positive increase in your y. This is what moving up means. Okay, what about moving straight to the right? Again, straight to the right is a positive dx dt and a 0 dy dt. You have to kind of go through all of these scenarios of what these things mean. How would you know whether you were stopped or not? What does stopped mean? Well, it's not a slope of 0, because the slope of 0 is just moving to the right maybe. Stopped is when both, again, if you're stopped, that means you are literally not moving. That means this guy is 0, dx dt, and dy dt is equal to 0. If both of those are 0, then you are stopped. If one of them is 0, then you're probably just moving left or right, or up and down, depending on which one is 0. Okay, so they like to ask questions about this. They give you information about dx dt or dy dt, things of that nature. I guess I want to go back up here one more time. Again, I just want to remind you that this still is concavity on the graph. Okay, so if you had some y versus x graph, and again, this isn't telling you anything about time, this is just your path length, and you knew you were doing this, that's concave up, that means that this whole thing will be positive. It's the time rate at which your slope is changing versus x changing with respect to time. So as you move to the right, what's happening to the slope? See how it's getting bigger? What's happening to the slope as you increase x? Nope, that would be a positive. And again, if this was negative, then your slope would be decreasing, just like it always is. Again, it's not really a new thing. It doesn't really affect too much in motion, but again, it's how you're changing your direction in this case. It's not acceleration, just like that's not speed. Okay, I think I kind of went through everything. I think maybe... Okay, let's do one more thing, and let's just look at the equation of a tangent line, just because I want to remind you how easy that is. So if they ever ask you in parametric, how do you find the equation of a tangent line? Remember, tangent lines are always just this. So if you want to find the equation of a tangent line, let's say you want to find the equation of the tangent line at t equals to 3. Well, you're going to have to find x of 3, you're going to have to find y of 3, and you're going to have to find dy dx at 3. So let's say you know that x of 3 is 5, y of 3 is 4, and dy dx at t equals to 3 is 10, then the equation of the tangent line is really easy. You just bust it up like you always do. Again, you can use this, or you can use y equals mx. So this is just y minus 4 equals 10 times x minus 5, like you always used to. Y minus 4 equals 10x minus 50 y equals 10x minus 46. Okay, so it's the same thing, the same requirement. If you want to write an equation on the tangent line, you have to know a point and a slope. Find a point. Sometimes it's given, sometimes you have to integrate for it. Remember, sometimes to find x of 3, maybe you know x of 1, and then you're going to have to integrate from 1 to 3 of dx dt, right? That'd be, if you knew x of 1 and you want to know x of 3, you'd have to accumulate horizontal velocity to figure out what you did from 1 to 3 seconds, add that to where you were at 1 second, and now you have where you are at 3 seconds. And then you could do the same thing for y. Again, you have to sometimes do some calculus to find this point. Do a little calculus dy dx, meaning dy dt over dx dt, to find the slope at that point. But then to actually write the equation on the tangent line is kind of going old school. Okay, hopefully this was a good summary of parametric equations and a calculus required, but all of those things, speed, velocity vector, acceleration vector, distance, displacement, position, slope, the second derivative, talking about moving up, moving right, moving with a certain slope, when are you stopped, all of those are questions that they can ask you, whether they give you dx/dt or maybe actually a decent number of times the given value is dx/dt comma dy/dt. They give you the velocity vector and have you go from there. But take a look at some of the problems and see if this helps.